This should be good. And we're good. Okay. Hello everyone. Hope everyone's weekend went well. This may be one of the earliest times that I've actually streamed before. But this was the best time that I found because I do have a lot of stuff to do. So I figured I'd do this week's stream right now. And then I'll make up for it next week with a few more streams because next week's schedule will be a little more free, which is going to be good. Let me turn this down. Okay, yeah, so today we're going to be continuing on with the shunting yard algorithm. This time we're going to be taking the reverse Polish notation that we parsed, and we're going to be putting it, we're going to be evaluating the actual expressions using using expression trees, which is pretty cool. All right, let me just make sure this is all going through. Okay, yeah, we're good. Okay, so we're gonna start with let's just get a quick recap of what we did. So if we go cd test and then run, let me actually just make sure that I put all the functions in there. Oh, I never did that. Okay, well, give me 2 more seconds. I just need to copy a bunch of functions in here because I never actually, or wait, did I? I could swear I did. Okay, yeah. Just give me, I'm just need to pull something from GitHub and then we should be good. Okay, now we're good. Yeah, so I inserted a bunch of these function tokens here. So we have sine, cosine, a bunch of trigonometric functions, some other functions here. And we can use these in an expression. So let's go over here, and I will type in this new expression here. So minus sine 2 pi cosine 2e minus the square root of 22 plus -1. All right, and then what I get is this reverse Polish notation here? I don't think this, is this right? Oh. Let me first print the token list to see if this actually works. -1 times sine of 2 times pi times cosine 2 times e minus square root of 22 plus a -1. Okay. I'm going to RPN this. Alright, let me test on my end to see if I'm getting the same results. Just give me 2 seconds. So dynamic array. Okay, I guess that's right. Alright, I guess this is right. Not entirely sure why this is right, but... Oh, you know why? Okay, I think I get this. Oh, this is definitely correct. Okay, yeah, I just didn't look perfectly correct, but it is correct. It's just my misinterpretation. Okay, now we can actually write some code. Alright, so we have our reverse Polish notation, which is this, and now we want to put this into our equation tree. So let's hop into shunting.c, and we already have our function definition set up for us. So we have rpn string, which I won't do right now. That's just, we don't even need this function. It was just there for debugging purposes. So I'll just skip that, but I'll probably put this in the GitHub push. Alright, so for the equation tree, we're going to start with our reverse Polish notation list. And let me just pull out one note. And when we first went through reverse Polish notation, we kind of noticed that there was this kind of format to it where you would pop, or you would take from the queue, or you would do whatever with the queue. So you would take an element from the queue, and then you would kind of just put them onto a stack, and then whenever you got to an operator, you would take the last one or two elements on the stack based on if it was a unary or binary function. So if it's a unary function, you only want to take the last element on the stack, and if it's a binary function, you want to take the last two elements on the stack. So let's see how this works. So we're first going to initialize our stack. So dynamic array stack is equal to dynamic array allocate, and then just default allocate. And then we're going to iterate through the list. So we're going to use an iterator here. So dynamic array iterator. It is equal to dynamic array iterator new. This is something from the dynamic array structure. And then we're going to keep track of a token. So sy token pointer current is equal to null. So then while cur is equal to dynamic array iterator next, passing a reference to it. So while this has while current is not null, so while there is another token to be processed. So while another token is to be processed, we're going to say if current.type is equal to constant, or current.type is equal to constant string. So if the current token in the reverse Polish notation is a constant, we're just going to push it to the stack. So dynamic array add last, a reference to stack, and then we're going to create a node. So sy create node with current. So we're going to create a new number node and push it to the stack. So we're essentially going to have a stack of nodes here. And I'll actually go through this process once again, just with this, or actually, you know, it'll make sense. But so essentially, when we look at this reverse Polish notation, we start with the 3. We start with the 3 push a number node. Then we go to the -2 push a number node. Then we get to the exponent, and we are going to create a node for the exponent, but the children of this exponent node will be the last two elements on the stack. So it'll be the 3 and the -2. So otherwise, if it's a function, as a function, to create a function node. So we're going to have sy token node pointer function is equal to sy create node, and pass in current as the node to be, or the as the node to be created. You know what we could do is just you know, this is fine right now. So we have our function node. Now we want to determine if we want 1 or 2 arguments. So if sy is unary, and pass in the token, which is current. So if it's a unary function, then we want to take 1 argument and put it on the left side. So unary function. So we want to say if stack.size, just to verify that there is an element. function dot left is equal to dynamic array, remove last, and pass in reference to stack. Just like that. Otherwise, binary function, insert two children. So the right child will be the second argument. So if stack.size, then function.right is equal to dynamic array, remove last, pass in a reference to stack. And then the left child will be the first argument. So if stack.size, then function.left is equal to dynamic array, remove last, and pass in a reference to stack. And the reason why we're going to be taking the second argument before the first argument is because this is a stack, and this is reverse Polish notation, right? So everything's kind of in reverse order here, but it's also because it's a stack. So the newer stuff will be on top, and the newer elements are the things that you get. All right, so that's that, and then we're going to say dynamic array add last, pass in a reference to stack, and then function. So if we look here again, when we create a node for the exponent that has the 3 and the 2 as a child, or as children, this is going to become its own node. It's going to become its own node A. And we looked at how that would work. Like right here, we saw how A would now become the node in the tree. So then we just follow the same process. A is now a node, or then the next token would be a 27. So we push the 27 onto the stack. Then we get an operator. We create a function node. We see it's a binary function. So we take the last two elements in the stack, which are going to be the 27 and the A, right? So B is equal to 27 times A, and A was another node. So we're creating this kind of tree structure using the stack. We're using the stack here to build a tree. And then at the end, what we want to say is sy token node pointer ret is equal to dynamic array remove last and pass in a reference to stack. And if there are no more elements, this will just be null. And then dynamic array free, pass in a reference to stack, and then return ret. So we're going to take the last element from the stack, and then, or let me actually just call free deep here, because if there are any more elements, we don't want to have pointers to them just left in memory. So yeah, token node ret and dynamic array remove last is just like that. So at the end, when we look at this, our last element in the stack will just be the f here, which is just e plus 1 in this case here. So e1 were combined into a node linked by the plus sign, and that just gives us one last node. So once we have processed all the tokens, we are left with an f on the stack, and f is the tree that we return. For evaluation, this is going to be, we're pretty much just going to follow the tree structure. It's just going to be a post-order traversal of the tree. We're going to evaluate the two children first, and then we will pass those results up into the function that is linking those two nodes. So we first wanted to determine which arguments we want to actually pass. So if tree dot t, or you know what, I'm going to do something a little clever here, or I'm patting myself on the back, but we can kind of simplify this a lot. So originally what I had was I had a bunch of if statements here saying if tree dot token dot type is equal to operator, or tree dot t dot type is equal to function, then we want to go, then if sy is unary, tree.t, then we want to say if then tree.left, then return sy eval of tree.t, evaluate tree, and we're going to call this recursively on the left side of the tree, so tree.left. And then 0.0 for the second argument there. And then something similar for if it's binary, so we take the two arguments. However, I'm thinking now, we can just make this one check, and then the recursive structure will take care of the null checking for us. Instead, all we can say is just if tree, then return sy eval on tree.t, and the left side will be evaluate tree.left, and evaluate tree.right. And then otherwise, return 0.0. So if the tree pointer is null, then it will just return 0. So if we have, for example, if we have a binary or if we have a unary function, the right node will always be 0 because there is no right node. So when we call this on a unary function, we will get some value for the left node, but then the right node will just go to this condition and return 0, which is what we want. So we kind of this is just a way to cut out a bunch of conditionals. So we can just remove that, and this function simply becomes evaluate tree. And this also will work for constants, because in the sy eval, this is the function that we're calling that we're going to write the definition for right now. In sy eval, we do need to check for types. So if t.type is equal to function, or t.type is equal to operator. And then here we have our checks for unary versus binary. So return sy is unary, t, question mark, sy evaluates unary, t and x, and then sy evaluate binary, t and y. And then else, if t.type is equal to constant, then return t.value.constval. Else, if t.type is equal to constant string, return t.value.named constant value.value. So once again, these are just the different token types that we have. We have a constant value which has no name. The named constant value is reserved for variables. And otherwise, we're just going to return 0.0. And we can also have a check up here, just if t, or if not t, then return 0.0. Yeah, so this evaluate tree actually just becomes one line because the recursive or the conditional checking of the tree pointer not being null will be handled either in the recursive check or in sy eval here. So when we call evaluate tree on tree.left, yeah. So if tree is not a null pointer, then we call evaluate on the tree pointer, which will go to this function here, and it will evaluate it based on the parameters we give it, and the parameters may be null or not. And if the left pointer is null, then we get a 0 for this return, and if the right pointer is null, then we get a 0 for this return, which is exactly what we want when evaluating constants which take in no parameters versus unary functions which take in one parameter versus binary functions that take in two parameters. Yeah. All right, so let's go ahead and let's test this out. So let's hop into main.c real quick. So we have our token list. We can print those tokens out. And let's say sy token node pointer tree is equal to get equation tree using the token list here. And then we're going to print out the result. So printf, and I'll do this to 8 digits of precision, so 0.8f, \n evaluate tree, and then we'll free up a bunch of the stuff. So we need to free the token list, and also sy free node on tree. All right, so let's clean this up, or let's run this. Okay. Cannot tell if this is correct. It looks correct though. I believe this is correct. All right, so let me put this in the calculator. So we have a minus sign of 2 times pi times the cosine of 2e minus the square root of 22 plus -1 is a minus 0.4964561,032, which is exactly what we got here, which is fucking awesome. Good shit. Let me actually test something real quick. Oh, okay, pretty cool. Awesome. Okay, so yeah, this is pretty fucking good. So yeah, that works. That's all that matters, really. So you can play around with that and see what you find. Try and break it, honestly. Because the only reason I found out that my last parser didn't work was because I tried to break it, and I did, unfortunately. But yeah. Okay, so that's evaluation. Let's add we're gonna now move into a little application here, and we're gonna be looking at variable registering, or registering a variable, like x or y, something like that, where we can store a value but also change the value if we wanted to. So we're gonna, our framework for how we store all this stuff is actually going to be very inducive to storing variables, since our constant tree, or our constants, are stored in an AVL tree, and this AVL tree can be modified. We can add to it, remove from it. We can do whatever we want with it. So yeah, this AVL tree was made to be dynamic, because we're going to be inserting and deleting from it a lot. So if we add a token or add a variable, it will show up when we call call the shunting guard algorithm on a string. So if we had, per se, minus an x, this would not like it because it can't find anything. So if I were to run this now, I would probably break it. But oh wait, actually, this thing actually just returns to 0 because it didn't find anything. So this still gives the right answer, but it didn't find an x in the constant tree, so it's going to return a 0 constant rather than a constant node or a constant token, which we could have. So we're going to have 2 new functions in shuntingyard.h. Return type boolean. It'll be sy register variable, character pointer name, and double value. And then boolean sy clear variable, character pointer name. And then we're going to copy and paste these signatures over. So if we're register variable, it's going to be a simple thing. We're going to see if there is a token that exists with the name. So sy token pointer t is equal to avl get, and the tree is constants, and the name will be name. If t, then we simply just want to set the value of the token. So t.value.named constant value is equal to value. So we just set the parameter value to whatever value is stored in the token here. And otherwise, we want to create a token. So to create a token, all we have to say is t is equal to sy create token constant string. The name will be the name and the value will be the value, those two parameters there. And then we simply just insert this into the AVL tree. So constants is equal to AVL insert constants name t. So constants is the tree that we're inserting into, name is the key, and t is the token that we're inserting as the value. And then we can simply return true. Well, we will return false in some cases, but right for now we're just going to be looking at this. And then for clear variable, we can simply just say something similar. We're going to see if the token actually exists. So sy token pointer t is equal to avl get, pass in constants and name. Then if t, then avl remove constants and name, and then else, or just return false. And we're going to return true if we did remove it. Or, yeah, so just return true. Now, I'm calling avl get beforehand just to check, because there's going to be a condition that we're going to insert next. But you could just say return avl remove name, or constants and name. But we're going to have an extra check just to make sure that we don't want to delete any required tokens like pi or e. But that'll be later on. So right now we're just going to get the token, see if it exists, and if it exists, then we're going to remove it and return true, otherwise return false. Alright, so let's try this. So let's register a variable. So if sy register variable, we'll register in the name x, and 2.0 is the value, and print registered into variable, and then else we can just print failed to register. So now when we alright, so let's try and do this without x first. So we run, we see that we get a value of 0.4964 whatever, and now if we do plus x, we should get a plus 2.0, and we get a 1.503, which looks right, and we see that the x was just inserted as another token, which is cool. And what's also cool about this is we can make this variable name whatever we want. We can make it xasdf, and if we register under that name, asdf, then it will still show up like that. So xasdf, and we still get the same result. Now, what if we wanted to change the value of like pi or something? Because pi is just another constant in the tree. So if we were to change pi to 2.0, and then run this, we're going to get something completely different, a different result. But, oh, you know why? Because xasdf is not registered, so it just took all 5 of these as separate variables. Okay, that's fine. So if we just deleted that, and if we changed pi to some value, we get a completely different result, which is incorrect. So we're going to want to kind of create a flag to restrict some variables like pi and e from being modified. So let's head into syutil.h, and in the constant, in the sy constant structure, we're going to have a boolean to say if this is restricted. And then this will just, we can just pass in this parameter to the constructor sy create token constant string. So there's a name value and now a restricted boolean. And then in the definition of the function, we can simply just paste in the parameter and then just set that. So ret.value.named constant value.restricted is equal to restricted. And then in shunting.c, when we call register variable, we need to make sure that this is not restricted. So in the if statement up here, so if t, so if the token exists, then we can register a variable. So if t.value.named constant value.restricted, then return false, because we don't want to modify value. Cannot modify restricted value. And then when we construct a variable in create token constant string, we just want to pass in false for restricted, because any token that you create will not be restricted. And then for clear variable, it's going to be the same thing. If the token exists, then we want to make sure that it is not restricted. So if t.value.named constant value.restricted, then return false, because we do not want to remove it from the tree if the value is restricted. What's up, Vicky-O? Yeah. So once again, just restricted variables you cannot modify. Now we're going to have a few errors up top because we didn't pass in a restricted value to create token constant string for pi and e, and for these two we do want to pass in a true for the restricted flag there, because we do not want these values pi and e to be modified. So if we run this again, we see that we fail to register and we get the correct value because pi is restricted. But that doesn't mean that we can't register in another variable. So if I copy and paste this over, and let's register into xc, and then at the end I'll minus an xc and run, then we get xc is 2.0, so we subtract 2 from the value, which was negative 0.49, and we get the same result, or the correct result, which is awesome. All right. There was one other thing that I wanted to do here. Thank you for the kind words, Vicky-O. Appreciate that. Yeah, like I've said several times, I'm in a bit of a buffer right now with OpenGL just because we did something pretty cool, but I will be returning hopefully next week. Later this week I will probably not be streaming. I can't stream at all pretty much just because I'm going to be clogged up with finals, but next week I will hopefully get back on the OpenGL train and see what else we can get up to there. Alright, then the last thing I wanted to do was just I don't know if I explained free node. I just kind of used that function here. But free node is it's a simple post order traversal of the token tree or the equation tree, just to free all the nodes, which is pretty self-explanatory. Okay, and then there was this last thing I wanted to look at, which is kind of a... Let me just see which one it... I guess there was something. No, it wasn't that. Yes, okay. I did want to add another function into syutil to be able to free a token list. So void sy free token list. This is just some cleanup. And here we would take in a dynamic array list or pointer list, and freeing this token list, I'm going to paste this signature over into syutil.c. Free token. In the free token list, all I wanted to do was since I can't just call dynamic array free deep on the list, and the reason why is because for example, when we have this list here, we have a constant, a 2, these can all be freed. However, when we have a token pi, I don't want that token to be freed. I want that token to be stored, the multiplication token, the cosine, the e. I don't want these tokens to be freed because we need them for later evaluations. So for free token list, I only want to free the values that are constants, and only constants, not constant strings, just straight up constants. So we're gonna iterate through the list here. So using an iterator, so dynamic array, or this is wanting me to include something. All right. Okay, I just need to include dynamic array, like so. So we're gonna have an iterator, dynamic array iterator. It is equal to dynamic array iterator new, and pass in list as the list to be iterated on. Then we'll have a current pointer, so sy token pointer current is equal to null. And then while cur is equal to dynamic array iterator next, and pass in a reference to it, so get the next element. And we only want to free this value if it's a constant. So if cur.type is equal to constant, then free the current value. And then we just want to free the list at the end. So dynamic array free and list. And this does not free any of the other nodes, which is good. Okay, and then in main.c, when we test this, we can simply, instead of calling dynamic array free on the token list, we can call sy free token list on token list. All right, so let's run this, just make sure there's no memory leaks. Debug, and just run it. All right, that exited properly. Good. All right. Yeah, this is a shorter episode. I kind of extended it more than I should have, but I did just want to put this video out based just for the variables. Yeah, an evaluation. So yeah, this is pretty much going to wrap up Shunting Yard. I'm going to rename a bunch of these functions because I really was super sloppy with that. But I will rename the functions, push that all to GitHub, but the code is going to remain the exact same except for the function names. And I think we're going to move maybe into some graph theory. I have a few things that or graph algorithms, stuff like that. That might be next with the mathematics library, but who knows? We'll see. I have written some code, but I still want to test it and make sure it's all good. But yeah, hope you guys enjoyed this. Hope you learned something, and once again, I will not be able to stream for the rest of the week, so I will see you guys next week. Take care of yourselves, be safe, and I'll see you then. Have a good one.